Yeah, good morning, all participants, and thanks for joining us today to that webinar hosted by Julabo company about the topic which we shared before with you guys about the new concepts of eco-friendly, energy-efficient chillers and their efficient sizing towards your application. So thanks again for joining us. My name is Frank Krebs. I'm responsible for the marketing part of equipment instruments in Europe for Avantor. And really love to see you joining us today. Before we start with Gary, our host today, I will just share some housekeeping notes. Like, you don't have to write anything down. The presentation, as well as a brochure as well, that will be shared together with a small survey right after that webinar. So there is no need to write something down. So we like to be interactive with you guys. So if you have any questions, don't hesitate to raise them using that question mark icon on the top right of the screen of your screen. Just raise your questions whenever you have some. We will take care. Neil and myself are happy to answer all of your questions, and don't hesitate to raise them. If something is wrong with your microphone or should be fixed, or you don't see us, just write me in the chat area. I will take care and advise you how to set up your system correctly, that you have the full visibility of Gary's presentation, which will start right now. Having said that, Gary, the stage is yours. Thanks again for your help for the webinar today. The stage is yours.
Thanks a lot, Frank, and welcome everybody. Thank you for taking the time to join us. My name is Gary Etherington, and just a quick introduction. I've worked with Yalabo either directly or with distribution or with customers of Yalabo for some 25 years, so I have a lot of experience in this field. If you have any specific questions, feel free to flag them. And obviously we want to make this as interactive as possible. So if I'm going slightly off topic, or if you want to focus in a certain area, please raise that at any moment with Neil or Frank, and they'll make sure that I'm aware of that. Okay, so let's get started, not waste any more time. So what I wanted to talk about is obviously with the drive for more increased sustainability and more environmentally friendly lifestyle across the board, there is some technological developments in the field of chillers, and I wanted to share with some of those developments that are here now and that are on the way that you'll be seeing in the market very shortly. So firstly, the first question I wanted to ask is, what is a chiller? Okay, because different people call chillers different things. So for us, for Yalabo, what we try and do is we try and separate chillers into two main areas. One is what we call really a dumb chiller. It's simply to replace where you would normally have tap water cooling. So that is, for example, a condenser or something that needs water running through just to cool down. The second type is where you're looking for slightly more precise control of an application. So that may be a sample or something that you're placing in the bath, in the fluid, or secondly, where you want to control the temperature of an external application, a reactor, a block of metal, or something like that. Now, in this presentation, I am going to focus mainly on the second type of application. The last set webinar we did with VWR, we focused on the first one, so I'm going to focus on the second one. So I'm going to ask Frank to flag up a quick poll, and I want to ask you your main areas of application. This may help answer some of our questions. Are you mainly putting your sample inside the bath, or are you mainly controlling the temperature of an external application? Okay, so an external application can be many different things. Okay, so our focus is the benchtop chiller. So either putting a sample in the bath directly, or like you can see in this diagram, controlling a reactor. Okay, so this tends to be much more precise than just replacing tap water cooling of something. I want to start with sorry, go on, Frank.
Yeah, results coming in. That is the only thing what I want to raise. So,
Okay.
so just give another 10 seconds or something, then all should have voted till then. Please share your. Okay, that's a result, Gary. I will share that. So
Okay.
it's a rough 50-50 percentage, internal and external
Okay.
split. So just for your information, I will close the poll now. Thanks for
Okay.
voting.
Okay, that's very interesting. About 50-50 is slightly different than what we normally see. We normally see slightly more with an external application like a reactor. Okay, so what I want to do first is just to remind people. I hope I'm not teaching people to suck eggs here, but to remind people of roughly how a compressor works or how a refrigeration cycle works. You start with a compressor, which you can see in the center of the picture, and what you're doing is you are compressing a fluid, a gas to a fluid, and that obviously liberates heat, and then the fluid will be pumped through an expansion valve right at the bottom of this diagram, and it will evaporate. And as it evaporates, obviously it's then absorbing heat or making your area cold. Um, so the important things, the important characteristics of this um, mechanical process is the fluid itself. So the fluid needs to be a liquid under modest pressure, okay, and it needs to evaporate under negative pressure. So it tends to be a gas at room temperature, and under slightly higher pressure, it will become a liquid. So one of the most important things on the choice of this gas is the environmental impact of the gas in your refrigeration circuit. So here's the second quick poll question is, do you know now in your chiller, do you know what type of refrigerant there is? There are two main types commonly used today, HCFCs or CFCs. Alternatively, you might know the R number. The poll is, are you aware of that now? So Frank, do you want to fire up that second poll for us?
Yeah, just a second. I have some. That is the type of.
Okay, I'm going to carry on, Frank, but you
Coming
can
up. Should
pop in
coming
as
up.
you get. Yeah.
Yep, comes up. Yeah. So please share your votes.
Well, just to give you an example of the evolution of gases. So the first refrigeration gases were developed or economically developed in the 1960s, and they were CFCs. So they had the R number R12, R23, and they were from the 1960s. And these were subsequently banned in the Montreal Protocol in the 1980s, and these were replaced by a family of CFCs called HCFCs, slightly different chemical formula. Our numbers typically ended in an A, so you typically had three numbers ending in an A, and these were introduced in the 1980s. And now in the 2020s, that is being replaced by what's known as natural refrigeration products. And they have the R numbers. R290 is a fairly typical one. Did you get any results back, Frank?
Yeah, yeah, it should be visible. Ah, no, you are the presenter, so it's not. So
Yeah.
HCFC, that was 30%, 10% CFC, and the R numbers are raising the top with 60% of the results.
Okay. Okay. That's really encouraging news because once upon a time people didn't know what gases they were. Okay. So why are the gases important? So the gases and the CFCs that were introduced in the 1960s are ozone depleting and they're also toxic, and they were banned from manufacturing in the 1980s. HCFCs are the gases that are predominantly used now since the 1980s, but they are going to be and are being phased out as we speak. Okay, so natural refrigerants are the next step. So what I wanted to do is explain how the gases environmental impact is measured, and that is to understand the CO2 equivalent. Okay, some of you probably know this. It's a relatively easy concept, and what it is 1 ton of the gas is equivalent to how much CO2 being emitted. So to give you a comparison of the three different types of gas we're talking about, um, CFCs typically have a number of in the region of about 10,000 CO2 equivalents. So 1 ton of R12 is equivalent to 10,000 tons of CO2. HCFCs, which are widely used today, currently being phased out, have numbers in the region of about 1 to about 2,000. R13 R134A, which is the most common, is 1,430. So 1 ton of HCFC is equivalent to 1,400 tons of CO2. Natural refrigeration, R290, is 3 tons of equivalent. So you can see immediately the benefits of moving to natural refrigeration. And so that you're aware, natural refrigeration is typically blended hydrocarbons, usually propane and butane. So it's called natural
Gary?
refrigeration. Yes,
Yeah.
sorry, go on.
Gary, sorry for interrupting you, but I
Yep.
just got a remark from a participant that he does not know which refrigerant he's currently using. How a customer can find out which one he currently uses?
Frank, brilliant question. And it brings me on to my next poll. Do you know to find out how the gas is inside your unit? Okay, so
Yeah,
the timing for that question is perfect. So
yeah,
thank you for that participant, and I was literally going to move on to the next step. Now, if you go to your
yeah.
chiller, now this is it doesn't matter if it's your fridge in your house, it doesn't matter if you go to your local supermarket and look at the refrigeration unit or your unit on the lab. If you look on the rear of the unit, you should see a shiny silver label like this. Okay, now that red circle is something I've added. Now, legislation has changed and it is now compulsory to have this, but most professional companies will have been adding this silver sticker for some time. And on the back of it, it will tell you the R number. If you can see, it says stage 1, it says refrigerant R290, and the filling weight 50 grams. And some of them will even have a GWP, which is the CO2 equivalent of the gas, which there says 3. Okay, so if you look on the rear of the unit, you'll see this silver panel and it should tell you the gas and how much gas is in there. So in this particular unit, which is one of our smaller units, you can see it only has 50 grams of R290 in it. Hopefully that is clear.
Yeah, it's very
Okay.
clear, Gary. And while you spoke to us, I just shared a poll, and it comes out, or it turns out that he's not the only one, that particular participant who does not know. 50% of our audience currently not knowing
Okay.
which refrigerant they are currently using. So I think that slide is very helpful for our folks in the call, I
Okay.
guess.
So, so what I'd encourage you all to do is take a look at this label on the back of your unit, and remember if it's two numbers like R12, R23, it's probably going to be CFCs. If it's R1 something like R134A or R143A, it's probably a HCFC, and if it's an R2, it's probably a natural refrigerant. But it also should have the GWP equivalent on there. Okay, so you should be able to find it quite simply, quite easily on 90% of all machines that were made after about 1985, 86 is when these labels started to appear. Okay, so it's not just the gas that is going to have an impact on the environment, on the sustainability of your chiller. Okay, so you have two things to think about. One is the refrigeration gas, and you can see there is a massive difference between a CFC, a HCFC, and a natural refrigerant. There is also the energy consumption of your chiller. Okay, so there are two sides to that. Most chillers, so benchtop chillers, these are ones where you put the sample in or you have an external application. They control temperature by two ways. And this is a very basic diagram of the inside of a bath. You have the compressor evaporating coil at the bottom of the bath, and then you'll have an electrical heating element to the side. And the electrical heating element usually looks like one of the old-fashioned kettle elements, just a metal coil with an electrical current running through it. Now, the vast majority of benchtop chillers, what will happen is the compressor will be working all of the time, constantly, and the electrical heater heats against that to maintain temperature. So if you turn the heater off, it would reach its lowest temperature. You turn the heater on to maintain whether it's -10, +10, whatever that temperature is. So what this does is you're obviously using electricity constantly um, on that heater to maintain temperature. You're also, obviously, there's wear and tear on moving parts, additional energy consumption. So the question is there an alternative to this? And this is where some of the new technologies are becoming available, and you will start to see them on the vast majority of our products are starting today available with frequency control compressors. So what this is, if you go back to if you think of the original diagram I had to you how a compressor works, um, it is pumping constantly. With a frequency control compressor, you have slightly more sophisticated electronics so that the speed of that pump is adjusted depending on demand. Okay, this gives you two significant advantages straight away. First is you're only using the pump when it's required, so you don't need to use the heater at the same time. So you're using significantly less electricity, up to 70%, depending on your particular application. Secondly, because they're working at lower speeds, there's less noise going into your environment. And then obviously it's natural because there's less moving speed, you have an increased lifespan of your compressor. So just to confirm that again, is you are using typically 30 to 40% less electricity, up to 70% depending on your application. So a dramatic increase in the CO2 of just energy consumption. So the other thing I want to ask you is how do you correctly size the unit? So this is something that as a supplier we quite often get. Okay, a client will pick up a brochure or look on the website and it will say, oh, I think we need this unit, please. And we like to have a conversation with you guys to make sure that you have the correct unit for yourselves. Okay, so if you're putting your sample inside the bath, so the first question you ask yourself, does it meet your temperature range? So you go onto a website, you pick the chiller, you say, I want to go between -30 and +100. This is perfect unit for me. But I just want to show you there are three completely different Yalaba units, all with roughly the same temperature range. Okay, so you can see the unit on the left is a fairly standard benchtop unit. The unit in the middle is slightly bigger, but it has a slightly larger bath, and you can see the dimensions of the bath are almost twice as deep going. Deep going into the lab wall, as it were. So you can have twice as many samples in there. But then the third example on the right hand side is much deeper as well. So when you are choosing a unit for a benchtop application, make sure you look at the usable bath dimensions and especially depth. We get quite a lot of clients who want to calibrate temperature probes, and they obviously need to think about how deep the temperature probe goes in the fluid under question. When it comes to external applications, again, you obviously have to start with your temperature range. But the second thing you need to think about is, does it have enough cooling power? Okay, it's a relatively simple mathematical equation. And this is something that you should learn at high school in physics. Okay, um, and this is the energy required is mass times heat capacity of sample, but don't forget the vessel or fluid in your bath. Quite often we have customers who think about, I have a block of metal that I want to control the temperature of, but they forget that you have 5 liters of fluid in your bath. The second thing to think about is heat losses to the environment, especially if you're cooling, your room temperature is going to heat up your block as well. Okay, and again, I want to use another example. We have 3 units here. They all look exactly the same. They all have the same specification temperature range, but you can see the difference in cooling power there. So the one on the left is only has 200 watts at 20 degrees C. It's probably going to be able to control half a liter reactor. The middle one is over double that amount of power, and you're probably going to be able to control something like 10 liters. And then the one on the right hand side has significantly more power than that. It has a 1200 watts, so that's 6 times the power of the first unit. So whatever you do, don't forget to think about the power. In conclusion, okay, a couple of conclusions I want to share with you is Yalabo has been the forefront of chiller development for 50 years, and you can see here a couple of really old units from predating even my time at Yalabo. Okay, Also, the current products offer a wide range of increased environmentally friendly tools for your application, not just CO2 equivalent as a gas, but you also need to think about the energy consumption of the chiller that you're going to be using for years and years in your lab. And I would encourage you to reach out to our vendor or to ourselves, and we will work with you to make sure that you have the right unit for your application. And with that, I would like to say, does anyone have any questions that they would like to share with the group that maybe myself and Neil can help you with?
I'm just checking the question area as well. I just got another one. Just give me a second, Gary. Yeah. So I would be very interested in a small chiller that can be used in the field. Wow, in Madagascar. That's a new country for me, at least,
Yeah,
where it is often, I can imagine, believe it or not, between 37 and 40 degrees.
yeah.
It should be preferably lightweight. Yeah, transportation issues, I guess, and able to cool down to minus 20%. Should it be Peltier based or battery driven? As yeah, he is not sure about the voltage he can make use of in the field directly of 220 volts. So he's not sure about, is it always given that power source, yes or no?
Okay.
Um, can you
Lots of
recommend something, Gary?
Yes, I can. Lots of interesting questions there. And what I would do is I would come back in a series of questions. The first thing I would say is with Peltiers, if you're going below, and it depends on the environment, okay? But if you're going below about minus 10, you're going to struggle. Okay, and
Mm,
especially when you have a high environmental temperature, a Peltier is going to struggle. Now, Ulabo does do Peltiers, but if you have an environmental temperature of above 25 and a demand below minus 10, I would say that a Peltier is not for you. So that's the first thing I would say. With regard to voltage, the advantage with the new range of frequency control compressors that we use, you can plug it in anywhere. Okay, so there is not a difference between a unit for 110 volts, for 50 hertz, for 60 hertz, depending on the load. So yes, I could make a recommendation that would work for that. Um, and I would take this offline and make a
mm.
specific recommendation asking what you're cooling. But what I would say very, very quickly is with minus 20 and an environmental temperature above 25, I don't think Peltier is going to work for you. With frequency control compressors, voltage and frequency is much less of an issue, and it should be possible to have an off-the-shelf product that is portable and usable.
Yeah, thanks for your answer, Gary. And I guess it's a good
Sure.
idea to come back that on offline to that specific customer.
Exactly, yeah.
Just give me a second. So don't hesitate to raise any questions. Um, while then questions coming in, it's a question from myself, Gary Moore, because that
Sure.
is what I was asked very often in my past, being a customer as well, is when you are still using a water jet pump with your rotary evaporator, for example, and you have some stuff at 7 degrees or something, what would be then your recommendation when it comes to that question? So rotary
Frank.
evaporator, not in a range, just a single
Okay.
one,
Okay.
and a water jet pump. Yeah.
Yeah, with that type of application, with a rotary evaporator, what you tend to need to have is something that just replaces tap water. So this is
Yeah,
more what we
indeed.
what we call an underbench chiller, okay,
Yeah.
which tends to be compact. The temperature control is not massively sophisticated because you only need plus or minus half a degree, for example.
Mm,
So we tend to call this rather bluntly a dumb chiller that sits under the bench, and
yeah.
the size, we have a range of those, and it depends on the size of the rotary evaporator, because obviously you can have a small bowl, or you can have up to like 50 liters I've seen recently. But also we very often do, and we have done this with VWR, we'll go into a lab that has a synthetic chemistry lab that will have 10 rotary evaporators, and we do one chiller and we split the flow between all of them, or we do a couple of chillers to split between half a dozen each. So it depends, and this is where the size of the chiller becomes really, really important, because
Mm.
you may have a 250-watt chiller that can do one rotary evaporator, but then if you put in a 2 kilowatt chiller, you can do 4 or 5 rotary evaporators all at the same time with a single chiller.
Yeah, that's good to know, Gary, because that are one of the most questions I received in my past, to set it in a row as well, to save space, yeah, precious
Yeah,
space at the customer. So
it
so
saves
here for
space. It obviously saves funding and power consumption as well, because obviously running
mm,
one chiller is, as opposed to 4 or 5, makes a big difference.
cool. Okay, let's just check again.
And what I would do to all of you guys is if you have a specific application, if you have a problem as such you need solving, is reach out to your Avantor guy, and they will obviously, if they need our help, they will speak to us, and we can come in, have a look at it, and say, okay, you have 2 or 3 options here, and this is what we would recommend.
Yeah, that makes perfect sense to me, Gary. And thanks already for your efforts sharing that valuable insights with us today. For other participants, thanks again for joining. And as said before, within the housekeeping notes, we will share that presentation and the recordings with you right after the webinar, together with a small survey. And don't hesitate to reach out to us with any questions that might appear later on in your daily lab, yeah, which will be obvious, right? So the questions come in when you are working in your lab environment with your specific application. So don't hesitate to ask us there. And for all other inquiries, reach out to us and to Labo. We are here to help you with your daily struggles. So please go ahead with that. Having said that, again, Gary, thanks for giving us that insights today. And thanks for joining us today and spending your precious time to the audience. And you will receive quite soon a follow-up mail with all the information given by Gary today. Thanks again for joining, and take care as always. And goodbye.
Thanks a lot, guys. Bye.